So what I will talk today, I plan first to explain the semi-infinite construction of representation of lattice vertex algebra, what I'm talking about, and maybe also I present finitization. And finitization, it means it is finding in such representation some pieces, whereas and character of these pieces in some simple case, in this case, is in a very simple case, coincide with the Jones invariant of some nodes, and it is maybe the first example where the topology Anyway, let me start with this, and what I discussed yesterday. I talked about the representation of the Clifford algebra, and maybe a more handleable and simple way to deal with this or to understand this is following. Well, in my Clifford algebra, I had generators psi I star and psi I, and I have representation W, which defined by annihilation properties that some vector annihilate by this psi and all other generate all W. Yes, but semi-infinite construction of this, it is surely well known, but it is good to say what is this. So let space, later it will be a function on a circle all around polynomials, but denoted by some V now. Yes, it will be just space with where psi I is the basis. Yes, and I recall belong to Z, and so if I consider an exterior power of V, then basis here is psi I1, psi I2, and so psi IN, where I1 less than I2, and so on. Maybe standard choices will be like this. And then if you surely in this place you can put infinity minus some I, V, and so what is this? And we do not understand surely such kind of object first of all has not meaning, but a naive point of view is working. We can just write down the infinite product, how to denote infinite product of psi I, and such that we have I numbers of holes. So it may be like this, psi something infinite tail till say something d some psi 4, psi 3, and then some gap. So it means psi 2 does not exist. Then next it will be psi 1, and so on. And so this is infinite product with the gap here, and we can have finite number of these gaps, and it is surely well known that we can write down psi standard notation maybe like this, summation in I. And so what is this? So because it is 1/2, I have in mind that such kind of infinite product surely can be written, but we have tail, infinite tail only in one side. So it can be like this. It is from positive, it is going still 5, and here 6, and so on, and 4, maybe 3, and this is typical element of this space. And this can be something, maybe minus 100. Anyway, the bases in this space are just such kind of products. And we can take all of them. So all such products which stabilize to infinite tail in this direction and to 0 to this direction, it will be the basis in all this space. And you can ask me, what is I? I, it means, in this case, we just need to make some choice. And for example, we can say that this dense things, dense product belong to this space, just plus 0. And this number count how many psi's we have. And now we have infinity over 2. And if I write down here, for example, I add one more thing, and it is lying here. And if I remove one of them, then it is lying here. Yes, but for example, what elements are lying here? I can take this psi and move in this direction. Yes, and for example, right, minus 100 here, and then I also can move and so on. Anyway, by this way, I have such space with this basis, and it is good way to understand the representation of Clifford algebra, because Clifford algebra acting in this space by the evident way. And for example, element psi I are acting just by product. I add one psi I from this side and put it in correct position if I want to write it in the ordered way, and it will be nice. And also, if you are interested in action of psi I star, it is also clear how they're acting. We have to look to this and finding psi minus I in this row. If we cannot find it, that it is acting by 0, and if such is here, I just erase it, and with sign plus 1 or minus 1, which is very easy to determine. Anyway, by this simple construction, we have a very, very explicit version of our space, and And also, it is good that we have here some elements of semi-infinite linear algebra where such kind of object appear by the natural way. Well, and this description make evident the following properties. That second one also will be important for me, but this is an irreducible representation of this Clifford algebra. Yes, but in order to talk about generalization, where we will have not so evident version of them, it is possible to describe this space, or at least formulate some kind of property. So on this space, we have the action of the following things. Surely psi I is acting, and I explain how they act. And also group Z is acting here, and an element of this group is just a shift. It takes this element of my space and then move it in positive or negative direction just by adding to this number element from here. And therefore, on my space is acting this and that, and surely they are not commute, and this is semi-direct product of Z over this psi I, where Z is acting here by also shifting I. Well, and such kind of algebra is acting here, and my representation is irreducible representation of this algebra. No, in this case it is very, very easy to check, and but still here, after that, it is some question. It means that to construct our space, we need only this algebra, but in some sense, this space and this algebra knows about the existence of them. And it is also possible to find them explicitly, but not so, not very simple, but not trivial. Anyway, and one more property, that the way to understand this space, it is possible to formulate it by which way? In this space, we have so-called external vectors. Who are they? Such kind of external vector, they are dense packing, and so it is some Vi is psi I plus 1, psi I plus 2, and so on. And what we can do? We can take Vi and we can act on this Vi by psi. Then what? If I act, all this psi are acting, all with this psi which are written here, acting by 0 on this vector. And so if I act by all psi I to this, and so what it will be? It will be C psi I minus 1, psi I minus 2, and so on till infinity, and then I acted to Yi. So in some sense it is natural representation of my algebra of psi I, which generate by this V, and annihilation condition is evident from this. And if we denote this space by, say, Wi, then we can say that W is the, no, we have embedding Wi can be embedded into W in my notation I plus 1, then Wi plus 2, and so on. And in the limit of this is just my space W. And so from this point, it is just a different way to say what I formulated yesterday, but let us go to the next example. My next example was following, that I had also Clifford algebra, but I had psi I1 and I have psi 1, 2. No, and surely also the element with the star, because it is Clifford. Well, no, first of all, surely it is not a big deal to repeat all this if we have indices here and such kind of construction is working. And it means that if we have, no, simple generalization is what? Here I had just Laurent polynomials of function on a circle, and I considering such semi-infinite things that no big problem to consider Cn times C the inverse and take semi-infinite things. It is like that. By the way, when, for example, no, it is knowing surely long ago, and for example, such kind of things are calling Dirac vacuum, so it means that Dirac knew surely the construction of such kind. But a natural question is, can we really work with tensor, semi-infinite tensor algebra? And no, in some sense, yes, but it is not. So if you really want to invent, for example, what is this, then no, it is possible, but the result will be not similar to this. Anyway, this problem is interesting, and in explicit construction of representations of affine algebras, vertex operator algebra, sure it is working, and we need it very much, and tensor product of such spaces also. Anyway, but I also constructed yesterday the current EZ, and which was psi 1z times psi 2z. Yes, and I discussed the question about this is some element of some algebra, or vertex operator algebra. But what is possible to do to repeat more or less this story, but replacing psi by e. So how to say it? That if we write down this, we can make up, no, this e is acting in representation, and so we can check that ez square is 0. Yes, in terms of component, it means that summation of E alpha, E beta equals 0 if alpha plus beta equal I. And if I want to really repeat this, replacing by psi by this E, what I can try to do? Well, I have EI. They have to be generator of some algebra. And first of all, they satisfy, I want them satisfy this relation. And this relation is infinite, so it is, we cannot think about this in the usual way, because it is some algebra where relation is infinite. But at least if you're talking about representation, and if this representation is representation of highest weight type, so it means that if we suppose, for example, it is not necessary, suppose that this representation is graded space, I want this be representation of this algebra and graded representation. It means that EG is acting from Ri to Ri plus G. Yes, and basically it is all, and I want that Ri be equals 0 if I is big enough. No, it is too strong condition, but at least if it is true, then it is clear that such kind of, so again, E give us commutative algebra, so E alpha and E beta commute, and also this is true. From such kind of infinite expression, infinite, but in such kind of representation, it gives us well-defined operator. So the fact that such kind of relation is hold, it is natural. Anyway, we are interested in representation of this algebra, and we restrict our self-representation of such kind. Yes, and also it can be some problem. We, in principle, even if we have such EI, we can try to describe the category of representation of such commutative algebra, of such kind of representations. No, it is an interesting question, but just category of such representation, nothing is known actually. Maybe not because I do not know any good application, but question is natural. But if we add these conditions, so if we add Z and such that I consider semi-direct product to EI, and I want the same property, so element from this, En, EI equal EI plus N times N, and his element from here. Yes, then in this case, what actually is known that such algebra has irreducible representations, and again, in this formulation, just to classify all irreducible representation with this condition. No, it is possible to do, but I think nobody did it. But what we can do, we can construct such representation by repeating construction of such kind. And this I want to say. Well, so just follow this line, suppose I want to construct a representation where I want to have extremal vectors. And such kind of extremal vectors, for example, with 0. I suppose that EI with 0 is 0 if I is positive. Yes, and I also want such kind of relations. And if I know only this, then I act this I to this vector, and so I get what? I get E minus 1, E minus 2, and so on. I have to factor what follows from that. And what is this? E minus 1 square, E minus 1, E minus 2, and so on. So infinite number of quadratic relation. Now, I know nothing about my representation, so in principle, if I have such vector, then this is a map from this to my representation. No, in real so I want to construct some representation, W, which at least have this. And then, if yes, then this is going on here, 1 from here going to V0, and in my examples, this map will be embedding, but we can ask first the question, what is this quotient? And about this quotient, it is not very complicated to study what is this. First of all, our quadratic relation, what they are doing. No, we have quadratic relation if we have E minus 1 square or E minus 2 square, for example. For next, this is a relation degree 2 minus 2, 3. Here it will be E minus 2 square, maybe 2 here. No, not 2 here, 2 here. E minus 1, E minus 3. Yes, and because I know this, and if I have some monomial in a quotient, I can rewrite such term using this relation. And using this relation, I can rewrite E minus 1, E minus 2. And so my relation gives me possibility. So if I have some monomial, then if I have some EI square, I can replace it by something, and if I have EI plus 1, I also can replace it by something. So therefore, I can remove from monomial such terms, and at least from that it is easy to see that monomial I1, I2, I3, and so on, IM. We do not know that we want, and actually it is true that they form bases. But right now we only can see that these indices have to satisfy Fibonacci condition. So it means that any indices repeated twice, and we do not like EI plus 1 also. No, in this case, direct consideration not big deal, and in principle it is easy to actually to prove that in a quotient the elements I1, I2, and so IS, where these belong to, surely they have to be negative, and also IS is bigger than IS plus 1 plus 1, yes. So this is Fibonacci condition. Yes, and no, it is one thing, and other things is what? That so this space is surely similar to this, so let us denote it, say, with 0. Yes, and let us look to this space. In this space, I have element with 0 times e minus 1 squared. And if you look to this element, then again from a relation we can easily see who annihilate this vector. And this vector surely is annihilated by the same that annihilate E0, E1, E2, E3. Surely annihilated because algebra is commutative and they annihilate this. But more than that, E minus 1 is annihilate this vector. No, first of all, no, it's not 2 here, or E minus 1. This is 0, so it is E minus 1. Here, and because of this relation, this element also annihilates this vector, and the E minus 2 also, because of this relation. Therefore, if we take this vector, so natural notation of this vector is W minus 2, and we can define the space which highest vector is annihilated by this, and then I can induce from this condition, and we get something similar to this, but starting with E minus 3, but no big difference. We do not know, but we have a map from W minus 2 to this. In a similar story in fermions, by evident way, says us that here such kind of maps are embedding, but here it is not so evident, and it has to be checked. But in this case, it is correct, and it is several ways of checking, but at least it is some work. Because we need some problems, yes? And because this problem is handleable, simple, relatively simple, and even can be found in literature, so maybe it is problem for people who need problems, simple problems. Complicated problems I also can formulate later, but complicated is complicated. But it is really simple. So we have, as a result, the same story as here. W0, but by the same way, I can see that it is a map from W2, then to W4, and so on. And from this side, I also can go, yes, and we have the sequence of embeddings, and on the limit of this, who is really acting? First of all, my EI definitely acting on this limit, and our relation is true because it is true on any component. Now about Z. Z is acting, but actually not the whole Z. So because we have actually map by 2, then on this limit is acting to Z semi-direct to EI. Yes, and again, maybe the part of this problem and or second problem that this direct limit is a reducible representation of this. Now, if you are talking about the semi-infinite construction, then no, because I explained, no, I not explained, but I claimed that in W, for example, the basis consists in element EI1, EI2, and so on with Fibonacci condition. Then in direct limit, from that we can deduce that in direct limit, the basis is given by similar stories. So what we have to do, we can draw the infinite lattice like that. And let us enumerate the points 0, -1, -2, 1, and so on. And then we can say about semi-infinite Fibonacci configuration. What is this? We have to put crosses somewhere. Like that. And such crosses, Fibonacci configuration, semi-infinite Fibonacci configuration is such kind of collection of crosses. And Fibonacci condition, it means that we dislike such fragments. Two crosses can not be neighbors. And they stabilize to 0 in this direction and to tail in that direction. To dense tail in that direction. And about tails, here we have two possibilities. Tail can go to odd numbers, like in this example, I think, or even numbers. So odd tail or even tail, so in principle it means that we have two spaces which differ by the structure of this tail, or we can consider them together. Anyway, if I have such configuration, then I can write the infinite product. For example, if I have something like this, I can write. No, it is in this case my tail is even, so it is 2, 4, and so on. I can write E-1, then E2, E4, and so on, till infinity. And it gives me something very, very similar to that. And well, as a result, I have two things. I have W even, W odd. Maybe I can sum up them. Maybe not on all this space. I have the action of EI, and also I have action of Z, which just again shift such kind of configuration, and also all this is irreducible representation of such things. And there how to say that here situation surely is not so simple as here, because you take this and you need to find, you want to find the action. So you want to calculate the product of this. Maybe, no, if you calculate product to say E minus 4, for example, something like that, it is not problem. You just added element here. But if you want to find something like this, then it depends. And no, in this case it will be 0. But in principle, in general, you need to make up some calculation. Now, using quadratic relation, and it is possible to do, but anyway, it produces some problems. So what my next statement? Next statement that such kind of construction, we have V even and V odd, and in my yesterday talk I said that, well, if I construct such kind of E by playing with fermions, so E is this, and such operators E which are acting in the representation of Clifford algebra or representation or corresponding semi-infinite form give us E which is satisfied to this relation. Yes, and you can find my irreducible representation inside this. Following, for example, the same logic, I can find in representation of Clifford algebra external vector and just embed these things into a representation of Clifford. Yes, but no, it's okay. But here, because it is semi-infinite things, I had also operators psi1 star z times psi2 star z. Yes, which I said that this and this generate this simplest possible version of lattice vertex algebra. And this guy is Fz. Yes, and the point is, the statement is that you can find, you can determine the action of Fi, which are expansion of this, on my space of semi-infinite forms, and which in this realization will be such operators, but in this abstract realization we just have to find what is this. And no, because you have explicit construction, it is possible to do, but it is not easy at all. And right now I only want to say that on this semi-infinite limit we can define the action of Fi, and we have the action of Ij, and they generate here, no, this Fi acting also separately here and there. And so algebra which generate Fi and Ej, so acting here, and this algebra gives us SL2 hat of level 1. So it means that up to central extension, if I take Fi and calculate the bracket of Eg, then it will be some Hi plus G, and central extension appear if I plus G is 0. But suppose it is not, then in this case it will be like that. It gives us some operators, and so this they commute, and they actually give us a Heisenberg algebra, but important point that Hi Ej is equal I plus J, maybe with 2 here, yes, and this is checkable, especially in such presentation. And here, if you manage to construct a phi, it is also possible. How to construct a phi? Maybe, no, because time is restricted, I postpone it. If it will be possible, I explain. Now, what else is going? So let us consider my W, and let me draw the picture of actually what is calling weight diagram of fundamental representation. No, I do it, but let me before present the following. Well, so in principle, such kind of construction and semi-infinite construction, no, because it is working so good in this case. So there are the natural question, maybe it is good to formulate. What are our possibilities? So right now I had fermions and I have commutative things Ez, which satisfy some conditions. So naively what we have here. So if you have Ez, surely we are working with Ez as series. It is Ei times Z minus I. Yes, and my algebra is actually, and my algebraic problem concerning algebra which generate by Ei. But if you look naively, what is this? How to think about this? You have line, this line of Z. In each point I have generator Ez, and if no condition and just commutative algebra, it means that in each point I have just generator Ez, and this Ez generate polynomial in one variable, and in a different point they commute. Well, how we can generalize this story? Surely by several ways, but naive way is following. So we can put in a point Z some more complicated algebra. So in this case, in a point Z is sitting this. Ez factorizing by Ez squared. But simplest natural generalization, I can put here some number, standard notation is k plus 1. Yes, and what is happening in this case? And can we make up the similar semi-infinite construction in this case? The answer is yes, and the space which we get by this way will be a representation of SL2 hat of level k. But what we can do also, so no, again, in all cases, the logic is the same. I construct some subspace which generate by external vector, take embedding, and so on. But they are more interesting examples. So here we have only one E, and no, because of some reason, surely it is much more easier to work with homogeneous relations, but not necessary. But let us restrict it by this case. Example can be the following: that we have to take E1z and E2z, and also suppose them be commutative, and we can replace such kind of relations by something. And if we want to get something reasonable, so we have to take maybe two polynomials as example. E1z, E2z is 0, or several polynomials, P2, and maybe more, even more, and also we can try to repeat the same construction. And now I wanted to say about only one example, that if we take E1z and E2z, and we impose the condition that E1z square is 0, E1z times E2z is also 0, and E2z square is 0, and so we will have now also commutative algebra, but generators are labeled by two things, 1 and 2, and to make up this construction, in this case, as a result, we get irreducible representation of SL3 hat, again k equal 1. Yes, and in my life, I tried to play in this game many times, and in principle, the problem is following. You have to choose, for example, polynomials P1 and P2, make up this construction. First of all, be sure that this construction is working, and then identify the result with some vertex operator algebra representation and so on. Yes, it is clear that it is a lot of interesting examples of such kind, but it is not studied at all. It is one of the interesting but complicated questions. Just take something and try to do this. Yes, but as for me, I want to return to well-known things which are known almost 25 or 30 years now. It is what is SL2 hat for bigger K. And as I said, let us consider the next case just to have some picture in mind. So we have EZ again, And it is not lattice vertex operator algebra, as I said. We return to lattice vertex operator algebra for bigger lattice a little bit later. But now it is easy, and we know, suppose that cube is 0, so it is the relations are looking like E alpha 1, E alpha 2, E alpha 3 is 0 if alpha 1 plus alpha 2 plus alpha 3 is equal to some n. And if you want to repeat all story for that, now it is more or less clear how it can work. And in principle, it is working. So because of these relations, it means that, again, let us try to repeat the same story. And you want to use this relation for rewriting monomials. And if in monomial I have something like EI cube, then I can change it to some combination of this. Similar story is happening of EI square, EI plus 1, and also the same for EI plus 1 square. So it means that Fibonacci condition is replacing by this condition. And it is possible to formulate by the following way. Let us, no, I skip these details, but only saying that what is going on. Again, we have lattice, and let us determine the configuration, but now which fitted for that. So it means that now in each point I put numbers, a0, a minus 1, a minus 2, a1, a2, and so on. But now condition will be the following, that ei plus e, no, first of all, such ei are integers, and ei, they are non-negative. And also our condition now is ei plus ei plus 1 is less than 2. Yes, and so this means that no, again, what I said from that, no, maybe I wrote it correctly. I do not like, again, ei cube, ei square, ei plus 1, it is like this. So if I do not want to take into account this, I need this condition. No, it is one thing, and then we want also such configuration be semi-infinite if in this direction it disappears, it is going to 0. In this direction it's stabilized to some tail. And what tail it can be? Tail is naively, and in this case it is correct, this is dense packing which corresponding to this. So what kind of tails we have? It can be 2, 0, 2, 0, 2, 0, like that. And we have two tails like that because they can go to even or odd. And one more possibility, it can be 1, 1, 1, 1, 1, 1. We have 3 different tails, and so we have 3 different spaces. And again, if I have configuration, I can write the product of E by a similar way, and they give me the basis in some space where A, which is satisfied to this, are acting. And the statement here is the following, that, well, we have three different spaces, maybe W1, W2, W3, which are in a correspondence of type of a tail. And we have EI, which are acting in each space. Surely we also have Z in this 3Z. No, it is not. 2Z, again, it is acting in each space. And just Z itself changes this and this. Because these two are corresponding to tails 2, 2, 2, 2, and shift move them. But this tail is stable with respect to a shift. So Z is acting here. Yes, and each of these spaces is irreducible representation of SL2 hat for k equal 2. Yes, and the similar story is for bigger k, and what is changing. So this condition is changing, it becomes bigger, 3, 4, and so on, but the same story is correct. Okay, I have 1 hour for today, and no, I want to, no, definitely today I announce at least something which related with knot theory, but before let me say something about character formulas. For character formulas, it means what? That suppose we are talking about this space. Then here it is a semi-infinite space, and if I want to have a character, character is trace of some operators acting here. No, if we calculate character, we need gradings. So in this case, we have two operators which are acting on this space, and these two operators here, they produce what is calling usually Q grading and Z grading. So each monomial, say psi0, psi1, psi2, and so on, it is some it is vacuum monomial, it is extremal vector, but each monomial, and this monomial also, it has two grading. So I want to connect with these two numbers, which can be maybe m and n. It is Z grading, and this is Q grading. Now, first of all, if you take this monomial, which is written here, grading have to be put actually by a more careful way. But I do not want to be very careful here, but at least for this monomial, let us, considering that Z grading for this supposed to be 0, and Q grading for this special monomial will be 0 also. Yes, but that first naive definition of this Z grading and Q grading. If you have, so in this case, configuration which we are talking about is what? It is 1, 2, 3, and so on, minus 1, minus 2, minus 3. Here configuration is just collection of crosses which stabilize in this direction and go to that direction. And so Z grading is the number of crossing and Q grading a sum of these numbers, not just number of crosses, some of these numbers which is written here. So, but this definition surely does not working, because here number of crosses is infinite, and sum of numbers here Q grading is 0 plus 1 plus 2 plus 3 plus so on. So it is not good, but what is well defined is relative grading. Because if we have two different configurations, that shows the difference of Z grading is well defined, and difference of Q grading is also well defined, because we subtract to infinity and get really well defined things. And so by this way we can define a character as a sum over all configurations, and Z here we have power this relative, but relative with respect to this, where it is both 0. So here it is a relative grading, and Q also relative grading, and it gives us a character. Yes, and if you really make up the standard exercise here, which is very simple, here in this case, so what is this? It will be the sum Q infinity is 1 minus Q, 1 minus Q square, and so on. And on the top we will have Z power I, and here it will be Qi times I plus 1, I think it is correct, over 2. Maybe minus here, but I think plus 1. Yes, and this will be a result of calculation here, and this is a character, and it is easy to see that by this way we calculate the traces of product of two operators which are acting here. Yes, and if you are talking about SL2 head business, or here, that from the point of view of pure combinatorics, it means, well, you have more complicated data here, but still you can do the same tricks and find out the characters. And the question is, what is the formula for that? Yes, there are two ways, maybe not two, maybe 10 ways to find the answer, and I want to use so it can be we can derive it from representations here of SL2 head, or we can derive it from algebraic geometry of affine flag manifolds which appear in my talk. Definitely, I cannot avoid it, but maybe not today. Or if you have such kind of description, you can derive it from combinatorics and from you can derive it from Brion theorem, which is pure combinatorics, and he used it in some toric geometry and things like that. But what is our question? That we have the following problem. Well, we have k plus 1, which is our parameters. We have configurations. Such configurations are just collection of AI. And we have condition that EI plus 1, it is, and all I is bigger than 0. So what is this? No, we have parameter k, we have collection of EI, it is infinite, but still it is collection of EI, and we have such inequalities. So what we're actually doing here, we have some infinite dimensional polytope, which is defined by these inequalities. We have integers point there, and we have to count this in. No, we have to calculate some kind of discrete integral over these points, and so in finite dimensional case, such kind of story is given by this Brion theorem, and this Brion theorem says the following. Suppose we have the data, but not infinite dimensional, but finite dimensional lattice, no, even z plus z we can take. And suppose Brion saying we have some polytope here. No, in his case, this polytope has to be convex, and vertices, suppose, for example, 0 is here inside, but it is, does not very much important. But what is important that vertices have to be at least rational, suppose even integer. Yes, and if I have such polytope, then first of all, what I want to calculate. So inside this polytope, I have integer point, and m integer point here. And the discrete integral or character-like expression will be the summation over all nm. They are integer point, and I can write something like this: zn1, z2m, where z1, z2 just variable or parameters and so on. So it means that I take such function and sum up by this way, or write down discrete integral. So you see that it is just, here when I calculate the character, I do just the same. Now what actually Brion saying. He's saying a little bit more subtle things, but we can say the following. Let us fix some parameter, say k, and I can take this polytope and suppose the vertices are something, alpha I. Then I can make up dilatation. I can put parameter k here. So if k is big, then our polytope becomes like this. It becomes bigger, 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 and bigger. And actually, Brion, what is Brion saying? That we can calculate what actually we want using quasi-classical way of thinking, just like more or less physicists are doing and so on. And the structure of Brion formula looks very nice. And so just let me write a little bit simpler picture. Maybe even like this is also working. Suppose my polytope is like this. And here just triangle and m n are non-negative numbers, and m plus n is equal less than k. And suppose I want, so this is just equation of this line, and suppose I want to make up such things. And the idea of Brion is simple. So we have three vertices, this, and this. And put the small person in each point. And suppose it is some person here, and some person here. And if k is big, they surely do not know about this person does not know existence of this person. Even more than that, he does not know that what he is living, where he is living is triangle. From his point of view, this is very, very far. And if he try to calculate the character in the vicinity of him, what it will be? It will be, his point is contribution of these vertices. This is, it is the sum of z1a, z2b, ab, just any integer which is bigger than or equals 0. So what he report to me, I am here, it is just this, it is 1 minus z1, it is 1 minus z2. If a person will be here, then what he is saying? First of all, his coordinate in this point will be maybe z2, I think, power k, because it is weight of this. But from his point of view, what he will see it is this. His cone, what he see. And if he make up the same calculation, his answer will be this. And it is 1 minus z2, I think, inverse. And here it will be 1 minus z2 inverse times z1. Yes, and this is what he is saying. This guy is saying that it will be z1 power k, and here it is 1 minus z1 inverse. No, we have to replace z1 and z2 here. It will be 1 minus z1 inverse and z2, it is like this. Yes, so we have contribution of 3 person, this, and this, and Brion saying that if we want to find the real answer, we have just to sum up their reports as rational functions. Yes, and the result here, it is not rational function, but it is polynomial. But if you really sum up this rational function, the result gives me the correct answer here. From one point of view, this kind of statement looks strange, but the proof is very simple. Yes, so, by the way, and it is what I want to say that if we apply this ideology to our configuration space, then the result gives us the correct character formula, and it will be fine, but maybe before doing this, let me say about something. No, there are such kind of arguments are working. No, again, this is really quasi-classical, and in the spirit and the really content of this is very close to what in some symplectic geometry and things like that is known Dustermat-Ekman theorem. In Dustermat-Ekman theorem, for the first glance, it is not the same, but where answer is similar. In Dustermat-Ekman, we calculate some integral, and we use the integral is exponent of something depending in some k, and if k goes to infinity, that first asymptotically this integral is the sum or fixed point or a critical point of functions, but under some condition this quasi-classical approximation is exact. So it means that quasi-classical, it means for the first glance it gives us asymptotic when k goes to infinity, but in reality we can calculate it after that substitute k some finite, and it gives us correct answer, the integral. And similar story is here. If I calculate sum of the contribution of these persons in the vertices, it looks and really is a quasi-classical approximation. Because if this k goes to infinity, that contribution of vertices, it gives us in some sense the leading terms of this expression, but the sum of these leading terms give you the correct answer. This is what statement here. And it is interesting that such kind of story is working in many not so evident situations. For example, what is, in a sense, combinatorial version of wild character formula? What is this? You have some Lie algebra, suppose SL3, to take the simplest possible case, simplest possible, not completely trivial case. Suppose we take irreducible representation with some highest weight lambda. Well, and if you take such a representation, then for representation we can draw so-called weight diagram. So this representation is also, no, because this is 3, the rank is 2. Therefore, it is bigraded, and the character is what? This is bigraded space, because Cartan is 2-dimensional. Then it is Mn. At what kind of grading appear, and the character is summation Z1 M Z2n, but here is the coefficient, because in a grading Mn it is not 1-dimensional space, but something bigger, maybe, but the character is this. And the weight diagram is usually the collection of Mn where this coefficient is not 0. And about weight diagram, it is known that, well, we have 2-dimensional plane, and while group, which is S3, is acting here, highest weight is somewhere here, and extremal vectors, highest weight is it is some lambda, and S3 is acting here, and no, better not to write down coordinates, because otherwise it produces confusion. Then vectors, extremal vectors are just 6 points, and Mn are here, and character is what? Character is again the integral, but function which is not so trivial here, because this coefficient it is something. Yes. But what actually Weyl formula says? Weyl formula says just the same things as this Brion. We can take this lambda and put some parameter k here. So we can, considering this polytope and the bigger, and bigger. And again, here we have vertices, and no, it is not Brion, because Brion does not think this. So some generalization of Brion existed, surely, and here in principle it can be more complicated things, but now I am talking about just general ideas. Again, if a person is sitting here, and suppose lambda is generic, then he is trying to calculate the character inside his vicinity. And the character inside his vicinity, because if lambda is big, that representation in the vicinity of this point is looking like Fermat representation. And therefore the character is top terms. We divide to the product, and similar story here, and here. But Fermat representation will be different because we have rotated by Weyl group. Anyway, as a result, we have some collection of rational functions, which is just like that. We sum up it, and Weyl character formula for representation, this is just it. Yes, and again, one more thing, it is, no, here it is some generalization of Brion-like, which at least I do not know precise theorem which can be applied here, but it is possible to do what? That in representation of SL3, or for at least for SLN, the vector in representation irreducible finite dimensional representation labeled by Gelfand-Zeitlin pattern. Gelfand-Zeitlin pattern is not very simple things, but they are integer points inside some polytope, very interesting actually polytope, which is calling Gelfand-Zeitlin polytope. And you can apply Brion to that. And Brion as it formulated by Brion. And it is possible, but the problem for that case is following. Gelfand-Zeitlin polytope is complicated and number of vertices is extremely big one. In principle, Brion saying that we have to sum up over all of them. But the function which we integrate is not generic but special. And it can be shown that the contribution of the most vertices is just 0. And the remaining part again give us the while type formula. Anyway, it is our story, but if we return to my case, then yes, then we can I want to apply Brion in a following situation. Suppose it is something like this, but it will be easier to me to consider the following polytope. First of all, let me forget about this tail. I want to work something like this space. Suppose I have 1/2 of my line, and suppose I have here, they enumerate by some way, maybe -1, -2, -3, and so on. Now, about my problem. My polytope will be simple, relatively simple, and in this case it will be the following. So I have maybe here I have -1, -2, -3. It is because I choose such numeration, but about A may be better write down like this: A1, A2, A3, and so on. Yes, and my condition still it will be infinite, but not so infinite like this. It is living in 1/2 of my story, and I want to what? AI integer as usual, AI and then non-negative. Yes, and my condition are following: AI1 is less than or equal to some L, and AI plus AI plus 1 less or equal some K. Actually, what does it mean? L appear because it is some tail which is going to this point, 0. And because it is some tail, it affects what is happening in the first point. But after that, my condition will be this. Yes, and after that, if I want to write down character will be just without these tricks with infinity and so on. Character will be what? summation over A1, A2, A3, and so on, AS, and it will be Z times sum of AI. No, it means that I can think about this, that I put particles on this line. I put A1 particles here, A2 particles here, A3 particles here, and this is just number of them. And also I have Q, and Q I count this A with weights. It will be the sum of I times AI. And these are the precise things which I want to count now. And I want to apply Brion to this. And the logic of applying is just the same. That no, first of all, L is smaller than K, otherwise it looks strange. But L and K I both sent to infinity by Brion way, and so I suppose to apply Brion, I suppose L be big and K be much bigger. Yes, and L minus K surely also big, always big. Yes, then the Brion-like expression, this is what? So again, if we look to this, it will be polytope, but again, the vertices, it has many vertices. But one thing, that contribution of almost all vertices to of Brion time formula will be 0. And the question is who are essential vertices. And essential vertices, it is not very complicated to guess who are they. One essential vertices is surely 0, 0, 0, 0. Next is L 0, 0, 0, 0. Next is L K minus L 0, 0, 0, 0. Next L K minus L 0, 0, 0, 0. No, right now I cannot explain, at least by understandable way, why we have to restrict only by these vertices. But if you try to do it by hands by yourself, it will be clear very soon. But now let us try to calculate the contribution of vertices. Well, and first of all, these vertices surely is the simplest one, and contribution of from the point of view of a person who is sitting here, it is he does not see these inequalities at all. So from his point, it is just polynomial ring. And character of a polynomial ring, it is what? It is 1 over, no, in my convention, yes, it is 1 minus ZQ, 1 minus ZQ square, and so on. It is like this. No, and it will be if I calculate this in this vicinity. Yes, and now what is going on in this case? In this case, what actually this person see, what I can do. I can add what I want here, 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 anything. But if I'm about L, I can only subtract something from L. Therefore, the contribution of this, what it will be? It will be z q power L, because it is weight of this. Then subtraction is 1 minus z inverse q inverse, because when I subtract, I'm doing this. All other terms will be 1 minus zq square and so on. It will be the next term. Now, more or less crucial things to understand what is going on here. Now, first of all, we will have here, we will have zq power L, it will be weight of this. About this, it is what? Zq square k minus L. Yes, and but what is going on here? No, first of all, starting with this, and this, it is still the same story. But let us draw this separately and let us look what actually we can do. L, k minus L, 0, 0, 0, 0. So in this case, surely what I can do, I can subtract something from here. So I can change, I cannot, for example, change this and yes, and subtract something here, some minus I here. I think, no, we definitely can do that, but we also can do what? We cannot add something here, but we can add 1 to here and subtract 1 from here. This also we can do. And no, I think it is not a mistake. So if I am sitting in these vertices, what I am seeing? I see cone. So I can add what I want to this, I can subtract from this, and I can make up this. And all what I can do is this. So any point in the vicinity of these vertices is a linear combination of them. So if yes, if you believe me, it means that what we have, if I write correctly, we have 1 minus z inverse, and here is q minus 2 also. It is a result of such subtraction. And here it is, well, first of all, such kind 1 and minus 1, it does not change z grading. But q grading, it changes. And because here it is 1 and here it is 2, then we have 1 minus q here. Yes, so no, I think it is clear how such things are written, and maybe it can be exercised or not, but everybody can go further. And the contribution of each vertices will be either such kind of product, and it will have terms which have opposite structure. It is like this. And it will have terms like 1 minus q, or 1 minus q, 1 minus q squared, and so on. Yes, and then I have to sum up all of them, but now in a case of usual Brion, the statement is that we have a polynomial which is discrete integral, and we write down this polynomial as a sum of rational functions. Each rational function is the contribution of the set. But now we cannot do that because our things is not polynomial. Therefore, it's also serious. Therefore, if we want this to have meaning, we have expand them in one direction. And after that, we get the correct identity. Yes, therefore, yes, and no, maybe all about this, but let me only say what kind of similar story, because it is simpler actually. So let us suppose I want to formulate the similar story, but on a whole line, and let us consider the situation which I make up some a little bit non-accurate statement, but again, my configuration now will be AI, still same condition, AI plus 1 is less than k, and suppose for simplicity that our tail it has the following structure: k0, 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 and so on. Yes, and I want to say that Brion type arguments working, and they're working by which way? Well, we have configurations, and I want to find the Brion type formula for the character by the same way. And this kitchen recipe is following. First of all, we have to guess or find or prove what kind of external vector we have to take and put this observer spy, I do not know whom, to this point. In this case, they are external vectors, and such external vectors, they are what? K0, K0,
0, k 0, and so on. And the numeration of points is 0, maybe 1, 2, 3, and so on. Yes, and after that, what the person has to do? He has to take the point where he's sitting, yes, and calculate the character in the vicinity of this point. It is not so complicated to do, but maybe now maybe it will be complicated to do in details because we have not much time. But what will be the result? The person main term which he finds is what? Is 1 minus q, 1 minus q square, and so on till infinity. Then it will be 1 minus zq, 1 minus zq square, and so on till infinity, and also 1 minus z inverse q, 1 minus z inverse q square, and so on till infinity. So, and here it will be in principle some z factor and q factor, which I do not want to write explicitly now, but just structure of this formula appear by more or less the same way. We just look what is going on in this vicinity. Yes, and after that we have to sum up the contribution of this by all possible tails. Tails stop to some point, so we have tails are numerating by z, and we have to sum up this contribution that give us precisely Weil formula, parabolic type Weil formula, to be more precise, to the representation. And if we make up this with the, if tail will be L, k minus L, L, k minus L, and so on, then if we make up precisely the same things, then the result will coincide with the usual Weil formula. Yes, and now a few words about what will be the next lecture. I want to analyze a little bit more this semi-infinite construction from a little bit geometric ways, such that we can work with maybe not flag manifold, but at least with Schubert varieties. And these Schubert varieties appear also. And I started today's lecture with promise to say something about not invariants and some simple formula. What I'm talking about is following, that people, I mean information about this I've heard from Zhenegorsky, and this is his old result, but even 8 or 6 years ago, he worked about not John's invariant, but Havanov invariants of the knots. But Khovanov may be also interesting, but let us say about Jones. And his result was the following. Well, we can take torus in three-dimensional space and consider so-called toric links, which is going on like this. Toric links is given by two numbers, say m and n. Yes, and m times like here and n times like here. And Jones invariant, it is some function in Q actually, sometimes more variables, but suppose only Q, and it depending in m and n. Yes, Jones invariant is a polynomial, and no, for Jones invariant, even for m and n, it is some formula. But in Khovanov case, it is more complicated. But even in Jones case, it is good to consider not these polynomials, but send n to infinity. And in this case, such kind of polynomial can, when n goes to infinity, it stabilizes and give us something which has nice description. And a nice description, it is the following. We have to take polynomials in x0, x1, and so on, xm minus 1. Yes, and then we have to consider the quotient of this up to quadratic expression, the summation of x alpha, x beta, alpha plus beta equal some s, and the s run from 0 to m minus 1. So we have to take m minus 1 quadratic expression like this. And now, first of all, it is good because it reminds us what we had before in this vertex operator algebra. But statement, it is not Zhenigorski statement, it is known at least 10 or more than years before him. But we have taken this, and this is graded space, and we have naturally graded. Naturally graded, it means that I suppose, is it correct? Maybe, no, I can make some mistake surely, but the mistake is not serious. I have to grade them by 0, 1, 2, n, and m minus 1, or maybe by shift by 1, this I do not know. After that, we get graded space. So each xi has grading I. So altogether it has, say, it is such kind of Q grading. And then we can calculate character, and this character will be the polynomial, no, not polynomial here, series, which is such kind of limit. No, this I want to discuss because this Zhenigorski result is really interesting, but if we start to discuss Khovanov invariant, in this case, I formulated, maybe just to maybe not everybody know, and that it is also in Khovanov invariant, but it has the description of similar kind, and so it is interesting. But at least this is simpler but still. And at least it can be explained in terms of Schubert varieties, Weil models, and things like that. And therefore, it is simple part of the story. Okay, I have to stop.